I don't have that data. I have to assume the center of the meter stick is at the 50 centimeter mark. But you should have empirical data about where the balance point is. Now, I think drawing a quick little picture is helpful. I don't care if you do or not. Because you have a picture, you can draw right on your picture if you'd like.
It was 50.5.
Okay.
Yeah, I mean, we took that. I just
That's fine.
didn't need that data, sorry.
So it's 50.5 was the center of mass location. Okay, so in this picture, it appears as though they chose 67 to be where the pivot point is. And then over here someplace, at 50.5 is the weight of the meter stick. Again, this is 67. But then it looks like there is a 100 gram mass placed right at the 80. So this is me just getting the data from the picture. So now that I have the data from the picture, I believe I can go forwards with the lab calculation. I'm going to treat the pivot point as the middle. And from here, I'm going to recognize that the net torque is equal to 0. The system was balanced. So I believe the torque on the left is equal to the torque on the right. A reminder that an individual torque is calculated by doing the torque arm times the force times the sine of the angle. Now again, we're going to put the left torques on the left side of this line and the right torques on the right side of this line. But truthfully, some of these torques are positive about the pivot point, and some of these torques are negative about the pivot point, and we're adding them and setting them equal to 0. That's what truly is happening. But I'm just going to go ahead and say that if this one is my positive torque, well, this one had to be my negative torque because they're causing it to rotate in opposite directions. Now, the truth is you have a method to determine direction. This one has a pivot, torque arm this way, and my force is downwards. That means that this torque is into the board. And let's see, from here to here, this torque has a torque arm this direction, the force is downwards, so this torque is out of the board. So you can make one of them out of the board positive or out of the board negative, you just choose. Either way, we're gonna set these torques equal to each other because they're supposed to sum to be equal to 0. So the first thing I have is I need to get this torque arm distance. It's from 50.5 to 67. Oh, you're gonna need some calculators here because that's what the value of R is going to be. So R is going to be the distance from 67 to 50.5. Now, I probably should do all of this in meters. So let's go with 0.67 minus 0.505. This is the torque arm distance. The weight of the meter stick is the mass of the meter stick times 9.8. And we assume that the meter stick was horizontal. That makes this the sine of 90 degrees. Please don't be like first period. First period absent-mindedly didn't check to see if their calculator was degrees or radians, but it shouldn't have mattered. You shouldn't need to be typing in sine of 90. You should know that sine of 90 is 1. The whole point of making it horizontal was so that we didn't have to worry about the angle too much. But first period somehow didn't do that and was doing weird stuff. Sine of 90 radians is definitely going to be different than sine of 90 degrees. We want this to be equal to what's on the other side. So I'm gonna look at this torque arm distance, which is gonna be from 80 to 67, or 0.8 minus 0.67. And then we have the size of this force. It's 0.1 kilograms times 9.8 meters per second squared times sine of 90 degrees. This is part one of your lab, and this is how you find the mass of the meter stick. So you work the numbers out and get M. I'll give you a second so you guys have a little hand in this and have practiced at least once. All right, Bikini Bottom got M equals 0.079 kilograms. That is exactly what I would expect. The meter sticks are between 75 and 85 grams, most of them. So that's perfect. I'd be happy with that. So, any question about what you have to do for the first part of this lab? All right. So let's go to the second part of the lab. The second part of the lab is a little more complicated. Not much, but a little. So here's our set of data. They have clearly put the meter stick balanced at the middle. And we have what appears to be 5 torques. 2 on the right side and 3 on the left side. By placing the balance point at the middle, we have eliminated the mass of the meter stick as one of the torques. So our pivot point right here, and I have a torque here, a torque here, a torque here, a torque there, and a torque there. All good? You guys see what we're doing here? This part of the lab is going to be done a little different. In this part of the lab, we're going to see if, when you calculate the torques, it shows that they are balanced. So I'm going to look at all of our torques and make some calculations. Now I could redraw it, and I will probably redraw it just so that you guys can see it. But in yours, if you just want to write right on top of your picture, that's fine. I'll be able to see it when I'm grading them. The only reason I'm redrawing it is because I think it's hard for you guys to see it in the room. So I'm going to put the balance point in the middle. There's a torque here, a torque here. Let's see if I can draw a little better. There's a torque here, a torque here, a torque here, a torque here, and a torque there. All right, let's get all these. We know this is, looks like 50.25 is kind of where that string is. You guys kind of agree with that? I guess you can see it, yeah, 50.25. So this one, this is 55, and this is 2 centimeters, so I assume that this is 57 on the other side, so I'm going to put this at 56. So 56 and 50.25. All right, this one, that appears to be 65, again, 2 centimeters, so that's probably 67 on this side. So I'm going to put this at 66. And that's a 200 gram, and that's a 200 gram. Let's see over here. That looks to be 41 and a half. Again, 2 centimeters, so 43 and a half. So I'm going to put the middle at 42 and a half. So 42 and a half. That looks like 33 and a half. So that's probably 34 and a half. So this is 34. My last one looks like it's, I'm gonna say that's 25. Is that okay with you guys? Mm-hmm. So 25. And although this one is 100 and this is 200, I can't see this one. 50? All right. So that's our data set. Again, I'm gonna break this in the middle, and we're gonna add up the torques on each side. And when we're done, we're gonna see if they balance. We expect the torques to be equal to 0 when we sum them. I suspect we'll be off a little bit, so let's see. Now, you can do this lab and leave it in centimeters and grams if you want. Your answers will all be the same. So I'm gonna convert to kilograms and meters anyways, but you don't have to. You can leave it all in centimeters and grams will be just fine. So let's find the first torque arm. That's gonna be this distance. So and remember, it's torque arm R times F times the sine of the angle. So I'm gonna have 2 on the right side. This is gonna be my right side. This will be the left side. So 56 minus 50 oh, I said I was gonna convert to meters. I did not. Come on, Mr. Shelton, say what you're gonna do. 0.56 minus 0.5025 times 0.2 times 9.8 times the sine of 90 degrees. That appears to be my first torque. Any question where I got any of that from? Pretty easy. All right, let's do the next one. The next one's gonna be this distance. So that looks to be from 0.66 back to 0.5025. That's also 200 grams, so 0.2 times 9.8 times the sine of 90 degrees. And that's it. That's the only ones that are on the right side. So I think we've done okay there. I'm going to switch over to the ones on the left side. I've got this distance first, which is going to be 0.5025 minus 0.425. Then that's 200 grams, so 0.2 times 9.8 times the sine of 90 degrees. Do I need to keep doing this, or do you guys kind of see what's happening here? So I'm not going to keep saying it out loud. You guys get busy with the button thing, and then in a minute I'll call on 5 tables because there are 5 torques. Let's go. Atlantis, give me one of them.
0.4214
For left side? I don't know. I'm asking you this question.
For the top one, 0.159.
Top one on the left or right?
Left.
0.159? Can anybody back that up?
I can back it up. The middle one is 0.159.
All righty. You're sure?
Yes.
All righty. Hogsmeade, give me another one.
On the left, the bottom one,
0.123?
Yeah.
7?
Yeah.
So 0.124. Bowser's Castle.
The top one is 0.1519.
1519. Yay. Alrighty. Hoth. You got two left.
Top one is 0.1127.
Alrighty. And Paradise Falls.
0.3087.
3087.
Yes.
Okay. Yes.
I don't understand why the number before the 9.8, isn't that supposed to be the max? Why is that changing?
Well, because this is 200 grams.
Oh, because, okay, got it.
Got it? All right.
Got it.
So, before we go any further, does anybody have a disagreement with any of these? All right, because, yes.
Why did you put driving license not 10?
Because it's a lab and we know that we're using 10 in most of our calculations, but we should be using 9.8 when we do things that are based on something that's happening in real life, and this is happening in real life. At the same time, it really doesn't make a difference. We're going to be setting these two things equal to each other, kind of. Do you notice how everything has 9.8 in it? Truth is, we probably could have left that out completely and still found the same answer. All right, so the left side, add them all up. The right side, add them all up. So, see, left side, 0.1519 plus 0.159 plus 0.124 gives me 0.4349 meter newtons. Does that equal 0.1127 plus 0.309? 0.4217. Now, these are much better than first period. First period was terrible. These look close. Right? The idea is, does the net torque equal 0? So we're asking if the left torque equals the right torque. To make this determination, you need to find the percent difference. So after you have calculated the left torque and the right torque, we do percent difference. And if you don't remember how to do that, you take the difference between the two numbers, 0.4349 minus 0.4217. We don't care whether it's positive or negative, so we just take the absolute value. We just want to know how far apart they are. And then we divide by the average. So this is difference divided by average. Now, I find the difference to be 0.0132. And their average to be 0.4283. And I get 0.031. So my percent difference is 3.1%. I think anything under 5% effectively demonstrates balance of torques. Anything over 5% does not. First period, the data we used, their difference was 23%. That did not demonstrate balance of torques. This is 3%. I'd say this one demonstrates balance of torques.